In 1.3, we're going to introduce the imaginary unit I. This section 1.3 is labeled complex numbers because once we take the imaginaries plus all the reals, it makes the big number system complex. All right, the base definition here is the square root of -1 is I, the imaginary unit I. If we were to take this equation and square both sides, the square and the square root would cancel out. We would have another truth that I squared is -1. These are the two big things to note on this. We'll use that a lot, that I is the square root of -1 and that I squared is purely just -1. A complex number is written in the form a plus bi. You'll see this a lot in the directions on your homework. It'll say make sure to express your final answer in the form a plus bi. Sometimes we have a real part and an imaginary part of our answer, and whenever they're put together, we always put the imaginary part second. It's always listed second. We can add, subtract, multiply, and divide imaginary numbers. So when we do so, I'll talk to you more about that. But before we do, let's talk about all the number systems that we know now. On page 106, there's this real neat diagram with colors to kind of help you wrap your mind around all the different types of numbers we study. So I'm going to give you, this is kind of a review of the old real numbers, and then we'll add in these imaginary numbers. But the real numbers have a lot of subcategories. So you see on the left-hand side of this chart, all these subcategories, and then on the imaginary part, well, there's just those. They're just one big category, imaginaries. Then when we take the real plus imaginaries, it makes the big category, what the section's called a complex. All right, so let's talk about these real numbers and break them down. The first type of number that we study is called the natural numbers. A natural number is sometimes referred to as counting numbers because it's, if you were teaching a child to count, or probably how everyone learns to count, they start with 1, then say 1, 2, 3, you count them, right? So regular first type of number that we talk about, the naturals. And there's infinite amount of all of these numbers, so the ... says you never get to the last number, right? You just keep on counting, always can add one more. The next type of number that we study is the whole numbers. The only difference in the whole numbers and the natural numbers is whole starts with 0. So whole numbers include 0. And so these will be concentric because everything that's natural is also included in the whole. The next category that we would grow out to would be the integers. Integers are the positive and the negative whole numbers. So they take in the negatives, no fractions or decimals yet, but all of these numbers plus their negatives. So say -2, -1, 0, and then the positive ones as well. But there's no fractions or decimals in the integers.
Are there fractions and decimals in the natural or whole numbers?
No fractions or decimals have occurred in any of these subsets yet.
What about negatives with the natural whole?
So the naturals wouldn't have any negatives in it. The naturals would start with 1 and then just go up. The wholes would start with 0 and just go up, and it's not till you hit integers that you add in the negative side. The next big system is the rationals. That's when you really break loose. That's when you get most of the numbers that we normally use in our regular life are the rationals. Rationals have the word ratio rooted in it. So a ratio means able to compare two numbers. So a numerator and denominator, basically a fraction. Rational is anything that can be written as a fraction. And you may want to write that out in your notes too. So they're anything that can be expressed as a fraction. So all the things below, and that's why these are written kind of concentric within each other. So everything that's natural can be written as a fraction. You just put it over 1. Whole numbers can be written as fractions, even 0. 0 over 1 makes it a fraction. Any integer, these negative and positives, put it over 1, expresses it as a fraction. So all of these inside ones we've grown out to are also rational. But then we add in some new things. You know, our traditional fraction, like a half and a third and 2/3 and so on. So traditional fractions, of course, they can be positive or negative. Repeating decimals like 0.66, repeating is 2/3, so a repeating fraction. Repeating, I should say decimal. Also, any terminating decimals. Repeating and terminating decimals. So again, the repeating ones, 0.66666, actually transfers to 2/3, and you can check that on your calculator. If you have your calculator with you, type in 2 divided by 3 and see that it's 0.666 repeating. And then if you hit your fraction to decimal button, a lot of calculators, most calculators have this fraction to decimal toggle button. If you get that 0.66 repeating from 2 divided by 3, you can hit the toggle button and it will move it back into a fraction. So if it is rational, the toggle button only works on rational numbers. This toggle only works on rationals. That's how you can tell if it's a rational number or not. If it can't convert it back into a fraction, then it wasn't a rational number to start with. So the rationals can always be expressed as a fraction. All right, and I'll be glad to show you that button on your calculator if you're not finding it. You may not have it, it's not absolutely standard. So anyway, anything that repeats will move back into a fraction, and anything that terminates, it has a place value, you can always express it as a fraction. Like if you type in 0.2556, okay, it stops. There's some way to write that back as a fraction, because that would be tens, hundreds, thousands, 10,000ths. That would be 2556 10,000ths. So you could convert it if it has a terminating place value. You can name that place value and write it as a fraction. All right, so terminating and repeating. All right, the next category is not concentric. It is the opposite of rational, so they kind of write it out to the side and they say it's irrational. The irrational numbers are the ones that cannot be expressed as a fraction. They are non-terminating and non-repeating. The opposite, irrational, would be the opposite of rational, right? So they're still reals, okay? We're still in the real number system. There's lots of subcategories. The main two subcategories of the reals are the rational reals and the irrational reals. Again, when we take all this together, that's what we call the real numbers. A lot of the rules that we do in algebra, they'll say all of these rules apply to any real number. When we did the exponent rules last week, we would say all real numbers. Let A be the base, A representing any real number. So all of these apply to the real number rules. Some popular irrational numbers would be pi and e. We'll use those, and those do have standard buttons on every scientific or graphing calculator. If you hit your pi button, it will not toggle. These will not toggle. You know, like I said about the fraction to decimal toggle button on a lot of calculators, if you do pi, it's not going to toggle to a fraction because these cannot be expressed as a fraction. And then another category that we see is any non-perfect radicals. Any radical that doesn't reduce out, like square root of 25 is really just 5. So 5 is over here. But if it's not perfect, not a perfect radical, then it won't toggle either. It cannot be expressed as a fraction. All right, so those are our reals. Now, the new category, today's lesson, is about the imaginaries. The imaginary numbers, they're real obvious because they always have an I on them once they're reduced. So they're I, or if they've not been reduced, they've still got a square root of a negative number under the radical. That's how you know it's going to be an I situation. So the imaginaries, and anything, all kinds of combinations of imaginaries. Maybe you got 2 plus 3i, so it's got a real plus an imaginary part to it. But if it's connected to anything with an I on it, we've moved over to the imaginaries. So, then when you take the imaginaries plus the reals, the whole thing is what we call a complex number. And that's all of our numbers. That's all of the types of numbers we studied. There's only one thing that, and I can't remember if we talked about this last week, there's only one type of number that doesn't make any of these categories, and that is division by zero. If we try to divide by zero, dividing by zero, zero in the denominator, is undefined. It's not imaginary, it's not complex, it's not a number, it's just not defined in math. So the zero in the denominator, and if you do it on your calculator, and every calculator is a different kind of message to you, but it'll say some sort of error reading. If you do 7 divided by 0, error, or not in the domain or something. All right, so those are our number systems. Now let's get back to talking about how to deal with the imaginaries and reduce them. So let's start with example 1. Okay, so now we've learned that the square root of any negative number is going to be imaginary. Here's how we break it down. Basically, the negative part under it becomes an I. We bring that out as an I. But to show it more specifically, we could think of this as being negative 1 times 16. The square root of negative 1 times 16 would multiply to be negative 16. This part we just learned by definition is I. This part reduces to 4. We usually write it in that order and call it 4i. But basically, the negative under the radical, and again it has to be a square root. The square root of a negative is the I part. So as soon as I see this as a square root, which these will all be like that, a square root with a negative, I'm going to say that's the imaginary part. It's coming out as an I, and then if I can reduce this radical, I should do so. 70 will not reduce. 16 was perfect. On C part, again I have a negative. The negative comes out as an I. This time the 48 will reduce. There is some perfect square. It's not totally perfect. The square root of 48 does not perfectly come out of this radical, but it will break apart into something that is perfect, and that is 16. We could reason that 16 times 3 is 48. I'm not sure that's overly obvious, so we'll talk about how you can find that, other strategies. But if you just kind of can break it down, just think of something, the largest perfect square that goes into that, that's the quickest way to get there. Then reduce that part. This looks weird, so we usually write the 4 in front, 4i radical 3. Or even put the I on the very back sometimes, but we definitely usually don't put it in the front. It just looks odd, I guess, there. So either there or at the end. All right. Let me give you a couple of U tries. I'm going to have you